Hi, in this recording, which I'm recording during my first block class, while they're working on their Nearpods and other fun stuff like that, you're going to hear about how to do Chapter 21. Now, the nice part about this stuff is that the vast majority of this is not on the Regents exam. That being said, it's something neat you should know, and therefore we'll cover it. Okay, so the first one talks about right-hand rules. It says vertical wire, so I'm going to draw that in. You have a vertical wire, which is carrying conventional current down in. So the current is flowing down like this. Now, we know that the current going down through will actually cause there to be a magnetic field, which goes circular around it. So we know that the magnetic field is circular around that wire. So the way we do this is via right-hand rule. So you take your right hand, and this may look backwards for you because I'm doing it my way, but my thumb is going to point down because that's the direction of the current flow, and then my fingers are going to curl around the wire. So I can tell that by my fingers are curling that it's going to be going clockwise. So the direction of the magnetic field is like this. So on the left side of my wire, so this side right here, my magnetic field is going to be pointing into the page. Now, this next one, a horizontal solenoid. Remember, a solenoid is just a series of current-carrying wire loops, as like this, coming towards you at the top. So this is going to be our second right-hand rule. So what's going to happen is my current, and I'll put this again in orange, is going to be coming out of the page towards you at the top and in away from you. So it's going to be curling kind of like out of the page towards the top, down away from the bottom. And so I'm going to take my right hand again, because it's always the right hand. And again, this is backwards, but my fingers are going to curl towards me at the top and away from me at the bottom. And when I do that, my thumb is going to point in this direction. And so my magnetic field is pointing to the right. Now, these next ones are all equations that I will give you, okay? Or if they're on the Regents exam, the Regents exam will have to give it because they're not on your reference table. So when you take my mastery checks and or the quiz or the Regents, these equations will have to be given to you. So what we do is we go through, we're going to guess again. So we have our Q is 5 coulombs of charge, positive 5. Moving to the east, so we have a velocity of 100 meters per second and a magnetic field of 0.4 teslas. And so I'm looking for the force on that charge. So my force, the way I find this is F is equal to QVB. This equation will be given to you if you ever have to use it. And so I'm going to be 5 coulombs times 100 meters per second times the 0.4 teslas. And so when I do all that, I get a grand total of 200 newtons. Now, because it is a vector quantity, though, I need to know the direction of that force. So what I'm going to do is I'm going to draw a picture here. It says that my charge, which I'll put here in a little black dot, is moving to the east. So I'm going to put that going this direction. So this is the direction of my velocity. Now, the magnetic field is pointing south. So my magnetic field, which I'll put in green, B, is going south. So to find out the direction, again, I'm going to use a right-hand rule. And again, this is going to be backwards for you because it's on the video. But my thumb has to point to the east. My fingers have to point down. So I have to contort myself just a little bit and try and put it in there. We go, like that. So I do it like this. And so in that process, since my thumb points to the east and my fingers are pointing down, my palm, which represents the force, is going into the page. So my force would be into the page. Okay, number 4, it tells us the force. So I'm going to write everything down here. Back to red. So we guess force is equal to 10 newtons to the west. I'll put that in W there as well. Is moving at a velocity of 4 times 10 to the 7th. That should be raised to times 10 to the 7th, not 107. Times 10 meters per second to the south. And he wants to know the direction of the magnetic field. So we're looking for B. Now you're like, well, but wait, I don't have enough stuff here. But remember, the fact that they tell us it's an electron tells us that we have pieces of information. We know the mass and the charge. Now I know I'm going to need the charge for this particular one. So it's going to be a negative 1.6 times 10 to the negative 19th coulombs. So remember, charge carries a negative elementary charge. So when I do this, my equation I'm going to use again is going to be F is equal to QVB. And so my force, 10 newtons, okay, is equal to Q, which is negative 1.6 times 10 to the negative 19th coulombs, times my velocity, which is 4 times 10 to the 7th meters per second, times my magnetic field strength, which is what I'm looking for. So when I solve this, I get a magnetic field strength of 1.86 Hang on, let me pause. I got to check this again. Sorry about that. I couldn't read my own writing, but when I recrunched it, it came out to be 1.56 times 10 to the 12th. And my units for magnetic field strength, remember, are Teslas. And it tells us up that above. Okay? But again, because it's magnetic field strength, it is a vector quantity, which means it must have a direction. So I know that my force, and I'm going to put this here, my force is purple, is traveling to the west. So there's my force. My velocity, which I will put in orange, is traveling to the south. And I'm looking for the direction of my magnetic field. So in this situation, again, I'm going to use, because it's a negative charge, I have to use my left hand. But that means my force is going to point to the west. My velocity is going to point to the south, so like that. And so my fingers are pointing away from me, so into the page. And so my magnetic field strength, which is B, oops, wrong color, sorry about that. My magnetic field strength, which is B, is got to be pointing into the page, so into page. Now again, I am not going to quiz you on these directions. You need to know that the magnetic field, that electric current carrying wires create magnetic fields. Okay, solenoids create a magnetic field that looks like that of a bar magnet, and the interaction of these external magnetic fields will cause a force beyond a current carrying wire and or a charge. So if we look at this next one, we use the combination of this. We have a mass, is what we're looking for. We know the charge, and I switch from red to black, sorry about that, is equal to 10e. So that would be 10 times 1.6 times 10 to the negative 19th coulombs. So that's going to be 1.6 times 10 to the negative 18th coulombs. And it has a radius of 0.5 centimeters. So I got to change that. So 0.5 times 10 to the negative second meters, and has a velocity of 7,000 meters per second, because I changed my kilometers to meters right off the bat, and on a magnetic field of 4 Teslas. Now, remember we talked about this. This is called the turning effect of the particle inside that magnetic field, because that force is always perpendicular to the velocity, which it gives us circular. So this is actually going to give us a circular path as such. So this force is not only centripetal, it's also magnetic. And so what I'm going to do is I'm going to combine those two equations. So FC is equal to FB. So mv squared over r is equal to qvb. And if I solve this for mass, I get mv squared is equal to qvb times r. So divide through, m is equal to qvb r over v squared. So this v kicks out with this one, and so I end up with qbr over v. And so I take those, so I got 1.6 times 10 to the negative 18th coulombs. I take my magnetic field strength, which was, and then I got 4 Teslas. I multiply that by my radius, which was the 0.5 times 10 to the negative second meters, and then I divide that by my velocity, which my velocity, remember, was 7,000 meters per second. And so when I do all that, I find it has a mass of 4.57 times 10 to the negative 24th kilograms. Right. Number 6, it asks for the force acting at 30 centimeter wire carrying 10 amps. So let's run this down. So we know we have a length now of 30 centimeters. And so I immediately change that into meters. So I go 30 times 10 to the negative second meters. I know my current is equal to 10 amps. Okay, and I have magnetic field strength of 2 Teslas, and I'm looking for the force. That's my question mark. This is the other equation, which I will give you, which is Philb. And so my current, which is 10 amps, my length, which is 30 times 10 to the negative second meters, times my magnetic field strength of 2 Teslas. And so looking for the force, that force is going to have to equal, in this case, 6 newtons. Now, because it is a force, it is a vector, therefore I need a direction. So if I draw this out, it has a magnetic field. So let me go back on the chest check My magnetic field was in green, so magnetic field B is going into the page. I can't draw this, I'm trying to draw three-dimensionally, so I'll do what I can. And we have a current carrying wire, so I got to draw my wire in here. There's my wire, and it's carrying current to the north. So my current, which I'll put as orange, as I, is traveling north, and we're looking for the direction of force. So again, we're going to use a right-hand rule here, in the fact that my thumb has to point in the direction of current flow. My fingers are pointing in my magnetic field, so it's up and 2 into the page. And so when I see that, my force is going to be to the west. Okay, so then it should be 6 newtons to the west. All right, and our last one is, again, using Philb. We know we have a force of 0.02 newtons. We know we have a current of 50 amps. Magnetic field, so B is equal to 5 times 10 to the negative 5th Teslas. We're going to know what's the length of the wire. So on this one, we're just going to, again, use Philb. F is equal to ILB. Remember, this is the equation we'll use whenever they are perpendicular to each other. Remember, maximum amount of force occurs when the things move perpendicular, and you get 0 force when things move parallel. So you've got a force of 0.02 newtons. Current is 50 amps. We're looking for L. And our magnetic field is 5 times 10 to the negative 5th Teslas. And so when I solve for this, I get my length to be a grand total of 8 meters. Okay, so again, quick reminder. These equations I will give to you if you ever have to use them, or they will be given to you in the problem on the Regents exam. Okay, the key things you have to remember, though, is that current carrying wires, moving charges, always create a magnetic field, and those magnetic fields, when they interact with other ones, will cause a force to happen. So I hope this helps. Have a great night. We'll see you later. Bye.